Welcome to our complete guide on torch.nn.Embedding. In this tutorial, we'll dive deep into one of the most fundamental building blocks of modern deep learning, the embedding layer. Our learning objectives are clear. We'll understand the architecture and purpose of embedding layers, master all the parameters and their effects, implement embeddings in practical applications, and finally optimize embedding layers for performance. Let's get started. Let me show you the architecture overview. Here we have a detailed diagram showing how embedding layers work. You can see the flow from input indices through the embedding lookup table to the output vectors. The embedding matrix acts as a learned dictionary where each row represents a dense vector for a specific token. Notice how the lookup operation is essentially selecting specific rows from this matrix based on the input indices. Now let's set up our environment with the core imports we'll need. We're importing Pytorch and its neural network module, along with NumPy for numerical operations, Matplotlib for plotting, and Seaborn for beautiful visualizations. I'm also setting a nice visual style and fixing the random seed to 42 so our results are reproducible. Let's start with the basics of how to use embeddings. Here's our first core example of creating and using an embedding layer. We're setting up a vocabulary of 10 unique tokens, and each token will be represented by a 4-dimensional embedding vector. The embedding layer is essentially a lookup table that takes token indices as input and returns their corresponding embedding vectors. Let me create some sample input indices, 1, 2, 4, and 5, and pass them through the embedding layer to see what we get. Perfect! As you can see, our input had shape 4, just 4 indices, and the output has shape 4 by 4, that's 4 tokens, each with a 4-dimensional embedding vector. The embedding layer successfully looked up each index and returned its corresponding vector. Notice how each embedding vector has been randomly initialized. These values will be learned during training. The embeddings have gradients enabled, shown by that grad_fn tag, which means they're ready for backpropagation. Let me visualize the embedding matrix to give you a better understanding of what's happening. I'll create 2 heat maps, one showing the complete embedding matrix with all 10 tokens, and another showing just the embeddings we selected. Here we can see 2 visualizations. On the left, we have the complete embedding matrix with all 10 tokens, each row representing 1 token's embedding vector. The colors indicate the weight values, with the color scale showing positive and negative values. On the right, we see only the embeddings for the tokens we selected, indices 1, 2, 4, and 5. You can clearly see how the embedding operation is just selecting specific rows from the full matrix. Now let's dive into the parameter documentation. This table shows all the parameters you can configure when creating an embedding layer. Let's explore the padding index parameter, which is crucial for handling variable length sequences. The padding index parameter is essential for NLP tasks. When we set padding_ix to 0, that index becomes special. It always outputs a 0 vector and doesn't receive gradients during backpropagation. Let me create an embedding with padding and show you how it works with a batch of sequences that include padding tokens. Look at the output carefully. Wherever we had a 0 in the input, which represents padding, the output is a 0 vector. This is exactly what we want. Padding tokens don't carry semantic meaning, so they shouldn't contribute to the model's computations. The other tokens, 1, 2, 3, and 5, all have their proper embedding vectors retrieved. Now let's verify the gradient behavior with padding tokens. I'll compute a simple loss and check which indices receive gradients. Excellent! The gradient at the padding index is exactly 0, while index 2, which was actually used in our input, has a non-zero gradient of 4. This confirms that padding tokens are completely ignored during backpropagation, which prevents them from affecting the learning process. Let's look at the max norm constraint parameter. The max norm constraint is a regularization technique that prevents embedding vectors from growing too large. Let me demonstrate this by creating embeddings with a max norm of 1, then manually setting some weights with large norms to see what happens. This is really interesting. Before the forward pass, we had vectors with norms of 5, 0.6, and 2.83. After passing through the embedding layer with max norm set to 1, any vector with norm greater than 1 was automatically scaled down to have exactly norm 1. The vector with norm 0.6 remained unchanged because it was already below the threshold. This constraint helps prevent gradient explosion and keeps embeddings in a reasonable range. Let me visualize how the max norm constraint affects a distribution of embedding norms. This will show you the before and after effect more clearly. These histograms beautifully illustrate the max norm effect. On the left, we see the original distribution of embedding norms, which extends well beyond our max norm threshold of 1.5, shown by the red dashed line. On the right, after applying the constraint, you can see how all norms are capped at exactly 1.5. The distribution is truncated at the threshold, with many vectors now having exactly the maximum allowed norm. Different norm types give us flexibility in how we constrain embeddings. Let's compare how different norm types affect the normalization. We'll use L2 norm, which is the default, L1 norm, and L infinity norm, all with the same max norm value of 2. Notice how each norm type scales the vector differently. With L2 norm, we get the familiar Euclidean distance constraint. L1 norm constrains the sum of absolute values, resulting in different scaling. L infinity norm constrains the maximum absolute value in the vector. Each has its use case. L2 is most common for general purposes, L1 can encourage sparsity, and L infinity ensures no single dimension dominates. Here's another visualization showing the training process for embeddings. This diagram illustrates how embeddings are updated during backpropagation. You can see the flow from loss computation back through the network to update the embedding weights. Now let's look at scaling gradients by frequency. The scale grad by freq parameter is useful when you have imbalanced token frequencies. Let me demonstrate with tokens that appear different numbers of times. Token 1 appears once, token 2 appears 3 times, and token 3 appears 5 times. This is fascinating. With scale grad by freq set to true, all tokens receive the same gradient magnitude of 2, regardless of how many times they appeared. Without this scaling, token 1 gets magnitude 2, token 2 gets 6, and token 3 gets 10. The scaling divides gradients by frequency, which prevents frequent tokens from dominating the learning and helps rare tokens get meaningful updates. Let's explore sparse gradients, which are crucial for large vocabularies. Sparse gradients are a game changer for large vocabularies. I'm creating an embedding with 1,000 words, but only accessing 5 of them. With sparse gradients, we only store and compute gradients for the tokens we actually use. Look at that efficiency. Out of 1,000 possible tokens, we only accessed 5, and the sparse gradient implementation only stores gradients for those 5 tokens. That's just 0.5% of the full gradient tensor. This becomes even more important with vocabularies of 50,000 or 100,000 words, where sparse gradients can reduce memory usage by orders of magnitude. Let me visualize the memory savings from sparse gradients across different vocabulary sizes and access patterns. These plots really drive home the advantage of sparse gradients. The left plot shows actual memory usage, where sparse gradients maintain constant memory regardless of vocabulary size, while dense gradients scale linearly. The right plot shows memory efficiency as a percentage. When you're only accessing a small fraction of your vocabulary, like 5 or 10 tokens out of thousands, sparse gradients can save over 99% of memory. Now let's look at creating embeddings from pretrained weights. Often we want to initialize embeddings from pretrained vectors like word2vec or glow-v. Let me simulate this with normalized random weights and show you how to create both frozen and trainable versions. Perfect! We've successfully loaded pretrained weights into our embedding layer. By default, from _pretrained creates frozen embeddings that won't be updated during training, which is what you want when using pretrained features. But if you want to fine-tune them, just set freeze equals false and the embeddings become trainable. Let's look at a practical example with simple word embeddings. Here's a practical example using actual words. I'm creating a small vocabulary with common words like they, cat, sat, on, mat, dog, and stood. We'll map these words to indices and process some example sentences. Excellent! We've successfully converted 2 sentences into their index representations and then into embeddings. The first sentence has 6 words and produces a 6 by 8 tensor, while the second sentence also has 6 words with the same output shape. Each word is now represented by an 8-dimensional dense vector that can be used in downstream tasks. Let's visualize the similarity between our word embeddings using cosine similarity. This will show us how the randomly initialized embeddings relate to each other. This heat map shows the cosine similarity between all pairs of words in our vocabulary. The diagonal is always 1 because each word is perfectly similar to itself. The other values show varying degrees of similarity between different words. These are random initializations, so the patterns don't reflect semantic meaning yet, but during training, semantically similar words would develop higher similarity scores. Now for something more advanced, let's train embeddings with context. I'll create a simple model that learns embeddings by predicting the next word given context. This is similar to how word2vec and other embedding methods work. The model takes context words, averages their embeddings, and predicts the next word. Fantastic results. Our loss dropped from 2.24 to nearly 0 over 100 epochs. The embeddings have been successfully updated during training, learning to represent words in a way that helps predict the next word. This is the foundation of how modern embedding methods learn meaningful representations. Let me visualize the training progress and the learned embedding magnitudes. The left plot shows our training loss decreasing exponentially, indicating successful learning. On the right, we see the L2 norms of our learned embeddings. Notice how different words have developed different magnitudes based on their role in the training data. The padding token remains at 0 as expected, while content words have developed varying strengths. Let's consider performance implications. Performance is crucial when working with large vocabularies. Let me benchmark dense versus sparse gradients with a vocabulary of 50,000 words. Impressive performance gains. With sparse gradients, we achieved a 6.39 times speedup compared to dense gradients. This is because we're only accessing 1,000 out of 50,000 possible words, so sparse gradients avoid computing and storing gradients for the 49,000 unused tokens. In production systems with even larger vocabularies, this difference becomes even more dramatic. Let's look at common pitfalls and how to avoid them. There are several common mistakes when using embeddings. First, using the wrong tensor type, embeddings require long tensor for indices, not float tensor. Second, using out-of-range indices will cause an error. Third, when using frozen pretrained embeddings, they won't compute gradients. As we can see, each pitfall has been demonstrated. Using float tensor causes a type error, out-of-range indices cause an index error, and frozen embeddings correctly don't require gradients. Always use long tensor, check your index ranges, and be aware of whether your embeddings are frozen or trainable. Let's wrap up with a comprehensive summary and best practices. The key takeaways are that embeddings are lookup tables mapping indices to dense vectors. Padding index prevents special tokens from receiving gradients. Max norm constrains embedding magnitudes. Sparse gradients are essential for large vocabularies, and you can initialize from pretrained embeddings. For best practices, always use long tensor for indices. Set padding index to 0. Use sparse equals true for vocabularies over 10,000 words. Consider max norm to prevent explosion. Initialize from pretrained when available, and monitor embedding norms during training. Each parameter has its place. Use padding index for variable length sequences, max norm when embeddings grow unbounded, scale grad by freq for imbalanced frequencies, sparse for large vocabularies, and freeze when using pretrained embeddings as features. That's all for our comprehensive guide on Pytorch embeddings. Thank you for following along. You now have a deep understanding of how embedding layers work, all their parameters, and best practices for using them effectively in your deep learning projects.